Tucker Hermans. So Tucker got his PhD from Georgia Tech Institute. And then he did a postdoc at the Technical University of Darmstadt, which is where we met. And he's well known for his work on manipulation, particularly things like tactile sensing, in-hand manipulation. And we're very excited to see in the group of objects manipulation. He's now at the University of Utah and a founding member of the Robotics Center.
Yes. Yeah. Thank you, Ollie. Yeah. No, and thank you everyone for coming. I'm really excited to give my talk. And so the title I have up here, Improving Multi-Fingered Robot Manipulation by Unifying Learning and Planning, is what I thought I was going to talk about when I sent the abstract a few weeks ago. And it's still mostly what I'm going to talk about, particularly the improving multi-fingered manipulation part. And the other part's still going to be there. But like Oliver said, I have this recent work on multi-object manipulation that I'm excited about. So we're going to also talk about improving multi-object manipulation. And since all good things come in three, I also just threw multi-sensory in there since I have some stuff with tactile and some stuff with vision. So we're going to say that's multi-sensory for this talk. Right. And so in order of that is going to be the order of kind of the volume. Right. So I'm going to talk mostly about multi-fingered, a little bit about multi-object, and I'll kind of point at some multi-sensory stuff we've done. So I'm fundamentally interested in autonomous manipulation. And specifically, I'm motivated by the problem of robots operating in environments where they don't have models of all those objects they might encounter. And so Wally here is a great example of such a robot who comes across this object that he's never seen before, a Rubik's Cube, can skillfully pick it up, can interact with it, and learn its internal degrees of freedom. Right? And so the question that guides most of the research I do is how can we have robots that can fluently manipulate previously unencountered objects? And over the years, we've looked at this problem from a number of different angles. So one large area of work that I won't be talking about today is interactive object modeling. So we've done work on learning models of objects through pushing using vision, through touch, where we've built both 3D models and learned to recognize objects by their material. We've looked at how do we plan motions once we've grasped an object to build better 3D models of that object. And we're looking currently at using tactile sensing to infer dynamic properties of objects, so things like the friction, mass, center of mass, and inertia. Related to this is work I've done on learning with haptic and tactile feedback. So we've done work on learning to gently place and pick deformable objects, which you see on the left, where we don't have a full model of the object, but we can still skillfully manipulate it without crushing it. Work from my postdoc in the top right on learning to detect slip with tactile sensing. And some recent work we've done on learning hybrid force position control policies that have robustness to, say, changing friction properties of the material it's sliding on. Right? And so underlying all of these techniques are some combination of control or planning coupled with machine learning to handle uncertainty from the environment and difficult problems of modeling in the sensor space. Right? So these biotech sensors that we're using for tactile sensing, we don't have kind of accurate force models for, so we have to do learning to deal with them. Okay. But today we're going to talk about multi-fingered manipulation. And the first thing we think of in multi-fingered manipulation is multi-fingered grasping. Right? And you might ask, why do we want multiple fingers for grasping? Why are parallel jaw grippers not sufficient? And the first thing that you can see on your left, looking at the picture here from the Encyclopedia Britannica of human grasping, is multi-fingered grasp enable increased stability. Right? So if I'm a robot that wants to throw a spear, and I want to lift up this heavy spear that has a large moment at the end, I want to have something that's not going to rotate out of my hand like it might if I just have kind of 2 points of contact from parallel jaw gripper. But closer to what we're excited about is not just this increased stability, but it's increased versatility and dexterity. And this is what we can see on the other image here. Right? So in this stone tool flaking task, right, being able to delicately impart forces on the object and precisely move it is a really important thing. And we're going to be able to enable this more with multiple fingers than if we just rigidly clamp down on things and have to move it entirely with the arm. More so, not only do we want to just pick up these objects, but we want to do things with them. And so I'm also going to be talking today about multi-fingered in-hand manipulation. So if we want to do things like have robots use tools made for humans to perform tasks in their environments, we'd like them to be able to manipulate them relative to their palm, let's say, instead of fixed to the robot and then only relative to some external reference frame. Additionally, in-hand manipulation is helpful in tasks like grasping in clutter. So if I'm going to Oktoberfest and I want the robot to put some mustard on my sausage, then I'm going to have it pull out with this overhead grasp so it doesn't disturb any material on the table. But then if it tried to squirt it, it would get it all over its hand. So we need to perform some sort of in-hand regrasping to grasp it in such a way that we can correctly use this tool. Right? And so motivated by this problem, we're going to look at a few different ways of doing in-hand manipulation that aren't quite at this level, but we think are steps along the way to getting to this. OK. So I'm going to outline the rest of my talk. So I'm going to now talk about our approach to multi-fingered grasp planning, which we view as a form of probabilistic inference with learned models. I'm then going to talk about two different trajectory optimization techniques for in-hand manipulation, where we don't require full knowledge of the object's dynamic properties. And then I'll briefly talk about this work on graph neural networks for multi-object manipulation that I hinted at before. OK. So I'll say please do ask any questions throughout the talk that come up. I've picked some highlights of these works, but I don't have time to give all the details. But if there's something that's really bothering you, I'd love to share the answer. So don't worry, I'll manage the time appropriately so we can all get through and get out on time. OK, so multi-fingered grasp planning. So if we look very broadly at grasp planning, we can break it up into two approaches. One is what I might refer to as model-based grasp planning. So here we're going to assume we have some model of the object of interest, typically at least the 3D structure of the object in terms of like a mesh, but also often the mass, center of mass, inertial properties of the object, maybe also friction. In such approaches, we can take kind of traditional optimization-based planning approaches and identify grasps that will be successful in fulfilling some criteria like force closure or form closure. Okay. However, this doesn't scale to this problem that I was showing as the motivation at the very beginning, that of picking up objects we've never seen before. And so for the past 15 years or so, people have been looking more and more at grasp learning, where here I'm going to take some data of successful grasps, or grasps that a human thinks would be successful, and learn a model to say if they will work or not. Okay? And it's a very broad characterization. But the general form of grasp learning that we will look at, and that we're going to be talking about in my talk, is grasp classification. So for a multi-fingered hand, we might do this in the following way. We take some representation of the object, which I'll denote with this variable z. So that might be an RGBD image. It might be a point cloud. It might just be an RGB image. From our perspective, we don't care so much. And then we're also going to take some parameterization of the grasp configuration, which in our case is going to be a grasp pre-shape. So what that means is it's going to be the wrist pose of the robot, 6 degrees of freedom, as well as the first 2 joint angles for these 4 degree of freedom fingers that there are 4 of. Right? So that means we're going to posture the hand in an open configuration. And then we have a controller that's going to close on the object and perform a lifting operation. Right? And if it does that successfully, we can generate a label that this is successful. If it fails, right, we get a negative label. And so then we can set this up in a very standard supervised learning problem. Right? I give as input the object representation z, the grasp configuration theta, and I predict success y, true or false. And typically, we're also going to be predicting some confidence on that. Right? We're going to, instead of just saying it's true or false, I'm going to give you some probability of it being correct. OK. So this is a standard way of doing grasp learning. But a question arises of how do we then use this model at deployment to do planning? Right? I don't have a direct way of generating grasps theta. So if we look at the literature, a number of ways have been proposed to do this. The most common, particularly for parallel jaw grasping, is to require some sort of simple sampling. Right? Where I'm going to generate a lot of samples, evaluate them, and pick the one that has the highest score, right? The highest confidence of success. This is going to rely on some external heuristic or limiting assumptions in terms of how we do the sampling. Right? We can't search the whole space effectively, especially as we move on to higher degrees of freedom. Right? Like the 22 total that we have for our hand arm system. Okay. So an alternative that people have looked at is a regression approach. So I kind of flip that model, and I instead take an image as input and directly predict the grasp configuration. Okay? So this is useful. I no longer have to rely on some external planner. I'm going to directly generate my grasps. But there's two big problems to this. So first, we can't learn from failure grasp. Only positive grasp can be given as supervisory information. And so for example, in our multi-fingered data collection, in something like 1,500 grasp trials, only like 200 of those were successful. Right? So the vast majority of guesses are going to be false. So now you're back to requiring some heuristic or planner to generate more grasp, and it's difficult again. Additionally, these models implicitly assume that there's one best grasp for a given object, right, in terms of the image representation. And we know from both human subject and robotics experiments that that's not true. We often would like to select a grasp for the same object in different ways, conditioned on the task. So a very simple experiment you can do is you can put a water bottle down on a table and ask your friend to put it on the top shelf. And you're going to see them grasp it near the bottom of the object so that they can reach easily up. Whereas if you tell them to put it below, they'll grab at the top and go down like this, right? So completely unprompted, we'll generate these different grasps, right? And there's many other examples we could use. But we'd like to have a grasp planner that can be used for many different tasks. And so we don't want to make this kind of limiting assumption that regression has. So finally, you can do reinforcement learning, right? You can just end-to-end learn an entire policy for doing this operation of grasping and lifting. But there's two problems that we see with that. So first is it's inefficient with respect to data. You require many more grasping attempts to learn a successful controller. And additionally, we can't leverage things we already know how to plan. Right? So if we're doing this supervised grasp learning problem, I can do motion planning with any off-the-shelf motion planner I'd like, and just have to move to this final configuration, and I don't have to learn the entire process. So again, in order to make things scalable, we'd like to use as few samples as possible in learning. Okay. So this motivates our approach to grasp planning as inference. So if we take this model of a grasp classifier, we can view it as, from probabilistic terms, in the following form. Right? I have some probability of a grasp y being successful, so setting it to 1, conditioned on my grasp pre-shape theta, my input sensory information z, as well as the learned weights of my classifier w. And I'd like to maximize the probability of success over these parameters theta. Right? We can also just view this probability as exactly the neural network we learn for this classifier. Then I can perform an optimization over theta. Okay? And just use whatever off-the-shelf optimizer I want. And importantly, I can also add structural information here. So I can put things like joint limits on my problem. Right? I want to find this theta not only to maximize success, but it also needs to be kinematically feasible for my robot. So I'm going to add these simple bound constraints on all my joints. Then we can efficiently solve this using gradient ascent. Right? It's ascent because we're maximizing the probability. Right? So I can take a forward pass through my neural network, given some initial theta 0, evaluate the probability of success, and then efficiently compute the gradient using backpropagation. Right? Where we're taking the gradient with respect to the input parameters here, as opposed to the weights of the neural network as you typically would do. But we can still do this very efficiently with off-the-shelf tools like in TensorFlow or PyTorch or whatever your favorite deep learning library is. Okay. So we importantly don't have to require sampling other than a few initial samples to start this process. And we don't have to rely on any sort of external heuristic or planner to generate candidate grasp. Right? We've actually going to use the exact same classifier we've learned as the planner itself. So to validate this idea, we collected a data set in simulation where we had the robot attempt many grasp and see how it worked. We generated grasp here using a simple heuristic where we added some random noise for exploration. And like I said before, we got about 1,500 grasp attempts, of which about 200 or so were successful. In the original work we did, we had a neural network that looked something like this. So we had an RGBD image where we also extracted surface normals and curvature. We passed those through some convolutional layers. We then passed our grasp configuration through some fully connected layers. and then concatenated these together before passing them through further convolutional and fully connected layers to generate grasp success. Yeah?
Theta only encoding the pre-grasp control.
Correct.
So the final grasp.
We're going to have a robust controller we run, and and it's hard-coded, exactly. Okay. And because it's hard-coded in both the simulator and the real robot, what we're going to see is that we don't have to do any fine-tuning on the real robot, and that we can bridge the sim-to-real gap without any extra training. Yeah?
What point did you rate it as a time?
So we just, in a general supervised way, we generated 1500. We take this classifier and we train it where we have triplets of images, thetas, and success, all from simulation. OK. So here are some results in simulation for unseen objects. So I'm going to build this graph in 4 stages. So the first thing I'm going to show you is for all these objects, which the robot has not seen in training. How well does a heuristic do that just kind of aligns the hand to the bounding box of the object and tries to close using the same controller? And we get some baseline results like this. Okay. So if instead we take those same, we can generate, right, for a bounding box, 5 different grasps. If we take those 5 and select the one that our classifier was most confident in, we get these results. So we see that this is going to improve the grasping success for most objects, but not always, which really just tells us that our classifier is learning something that's mostly meaningful in terms of evaluating good grasps. If, however, we just sample 100 grasps and choose the best one, we, in general, do worse, right? Because the space is so large that even with 100 samples, it's hard to come across a grasp that's going to be very good. Finally, if we run our inference approach, we see we do much better on average. And for most objects, we're going to do, we have a large delta between just the heuristic and actually doing the planning, right? And I would say that in simulation, we initialized all of our inference procedures using the output of the heuristic planner. And so what that means is for certain objects, we had heuristic grasp that we know would fail. And we were able to correct those to grasps that were successful. Right? So this inference procedure is really adding something on top of just the learning. So motivated by this, we then extended this to real physical robot experiments. So we did most of our experiments on this 7 degree of freedom KUKA arm with this Allegro hand that I mentioned before. It has 16 degrees of freedom. So it's about 125% the size of your hand. So it's a little bit bigger. But we also did some experiments on the Baxter, which I'm not going to show you. But the main thing that I'm pointing out is just that while we are motivated by multi-fingered grasping, this approach will work for parallel jaw grippers as well. There's nothing fundamental about it that keeps it from using on other forms of grasping. Right? You can also use it on a suction cup or whatever grasping strategy you have, right? As long as you can get this input-output relationship that we talk about. Okay. So on the real robot, we did fewer objects. And also, we didn't compare to sampling because it performed so poorly in simulation. So here's our baseline result of the heuristic. Here's the maximum evaluation, again, generally improving. And then inference significantly improves beyond that, right? Where 3 of the 5 objects, we grasped successfully every time we tried. OK. So these are what some of the grasps look like. They work, but they're not the prettiest, right? We kind of have weird finger configurations on some of them, here and here. These other ones are maybe a little better. And I'm going to come back to this in a second. But first, I just want to briefly remind you of the contributions of grasp planning as inference. So by modeling our grasp planning problem as probabilistic inference, we can leverage deep neural networks for predicting grasp success from large databases that are accurate, but outperform sampling or heuristic evaluations in terms of actually leveraging this inference through the optimization. Additionally, we can embed other model-based knowledge into the grasp optimization problem. Right? So I showed how we could do it with joint angles, but I'm going to show you a couple of extensions now where we can add other knowledge, like collision avoidance, directly into the optimization and solve that without any significantly extra work, right? Since we're already solving this optimization. Okay. But so one other extension that we looked at is grasp type. So I showed you before those grasps didn't look that pretty. And while we don't really care about our robots looking pretty, we do care about this versatility of grasp that I showed before. And additionally, we want to make sure we can get precision grasp, where the robot's grasping with its fingertip, so that we can use this as an initial step in our in-hand manipulation task. Right? if every grasp I try is a power grasp, it's really hard to do in-hand manipulation. And we saw that both in our method and most in the literature, they would tend to generate only power grasps. And so we thought, how could we encode grasp type into this learning and inference procedure? So to do this, we did something very straightforward. We took our same model as before and simply said, for each grasp type G, I want to optimize over that as well. And all I'm going to do is I'm going to learn a separate classifier for each grasp type. Right? So I have grasp type 0 classifier and grasp type 1 classifier. So this say is precision, and this is power. Now I can do the same inference procedure, where I simply, if I care about just getting the grasp that works the best, I can optimize over grasp type as well. Or if I want to specify a grasp type, I can say which grasp type do I prefer, and then run the optimization. So in making this model, we made one further extension to our work, which is we learned a prior over grasp configurations. And we were originally motivated of this in terms of thinking of what is a good grasp shape independent of object. Right? Yeah?
What's the more formal definition of a grasp type? How are you?
So OK, that's a great question. So grasp types are generally, there's different taxonomies that have been proposed. For our work, we just have a human that's saying that was a precision grasp or a power grasp. And additionally, we have a different controller for closing the hand for precision or power. So in precision grasp, we try to keep the fingers extended, whereas in power grasp, they'll curl around the object. Okay. We're interested in learning these taxonomies, but that's going to require us to get more tactile sensing on our hand first, which is a project we're working on. Okay. So, right. So back to the grasp prior. We were thinking of this first in terms of we want something to encode grasp type, or not grasp type, but just grasp shape, independent of object. And this will also give us a data-driven way of generating initial samples to run our optimization with. Okay. But we found it had a more important use, which we had to deal with before with a slight hack that I didn't tell you about yet. But I can visualize this in a 1D example very easily. So if we think about our logistic regression output of our neural network, if we're maximizing this probability, we can look at it in 1D with this blue line. If I try to maximize it, I'm going to keep moving further and further towards infinity until the change in this value is less than whatever precision I set for my optimization to converge. Right? And so what we saw when we would run experiments is the robot would get a hand pose initialized here, and then would shoot the hand way out here in the optimization, because we never gave it negative samples far from the object, because we didn't want to waste our time doing that. So for the previous work, we added another constraint that the wrist couldn't move too far from the object. But now if we add a prior, which is visualized here with this green Gaussian mixture model density, and we maximize over the posterior, so the product of these two, right, the probability of success will quickly drop off as we move away from the data. And so this prior is a regularization term for our optimization that requires the robot to only try grasp that are close to those it's seen in training. Right. So by doing this, we can now generate grasp of both types, precision and power. So here we have the same object in each column, where on the top I'm showing 2 precision grasps, and the bottom 2 power grasps. And we see for similar poses, we can generate different objects, different grasps for the same object. So this is exactly what we were hoping for. I will also say that if we ever let it optimize over grasp type, so we said, I don't care what grasp type I want, just give me the grasp that's going to be most successful, every single time it selected a power grasp. And at first my student thought this was a bug, but it actually makes sense. Right? If I don't care about the grasp type, and I just want to pick up this object most reliably, a power grasp is generally going to be more stable, and so we should be more confident it will work. So there's actually a really nice feature of this approach in the end. Okay. So quantitatively, we compared here to both precision and power grasping. And so the comparison is first, like before I showed you a heuristic. So here's the heuristic of how we do for precision grasping. It's much harder than power grasping. So we have a lower baseline. If we look at our type 3 model, so the first model I showed, and just try to run our precision controller, where it's been trained on the same data set as this 2-type grasping model, we get this result. Okay. So it barely does better than the heuristic. However, if we use our type encoded model, we do significantly better. So we get this huge jump in precision grasping success by explicitly modeling precision grasping as a separate model from power grasping. When we look at power grasping, we see a similar trend. So here's the heuristic, here's the type free, and here's the type encoded. So the delta is less, but you can note that for power grasping, we now have a 100% success rate across all the objects we tested on. So just by knowing that precision grasp exists, power grasping becomes an easier problem. Right? We're simplifying the learning space into two distinct categories. So there's a simpler geometry to learn in terms of the decision boundary. Okay. So here's some video results of that running. So here's the robot reaching out and then trying a power grasp on this mustard bottle. Okay. So now we're going to, in a similar pose, try a precision grasp. And we see it's successful as well. I would say that these grasps take about a second to plan, so they're still quite fast. We might be able to speed that up further with a little bit of optimization of the neural network structure. But they're not taking minutes, as some grasp planners do. Okay. So you can see more examples of this on our website, but for the sake of time, I'm going to stop it there. So one other extension that I wanted to tell you about our grasp planning work is more about encoding more knowledge into the structure. So if we take any of the models I showed you before, how can we improve the optimization with one of these classifiers? And so one thing we looked at doing was we'd like to encode geometry into collision avoidance for the planner. So in particular, if we take a partial view of the object, shown here as a point cloud, that we get from, say, the Kinect camera we're using to extract our features for the neural network, we'd like to learn a 3D object reconstruction of this object. However, we're going to learn that 3D reconstruction in a very specific way. And that is as a signed distance field. Right? So if I learn a function that for the given object O and parameters of that neural network theta, I can evaluate for any point in the 3D space the signed distance. Right? And I want a signed distance function because we know how to use those to do collision avoidance in motion planning. Right? I can use all of the tools from trajectory optimization to directly encode this as a constraint in my optimization for grasp planning. And so we can do this. We can learn a single feed-forward neural network where we've used something called point-conv to encode the point cloud efficiently into a structure that we can run convolutional neural networks on. And we can generate as much data as we want synthetically of these point clouds, where we can have accurate noise models of cameras and simulate a lot of points in the space and get the signed distance field. Okay. If you want, we can then mesh the output of the signed distance field by finding its zero level set and generate an object mesh. But from our perspective, the signed distance field itself is much more useful. So we can use that now in our same grasp optimization, where we have a slightly different neural network this time that's taking this same point structure as input for its feature representation. We have a prior again. You see we have our joint angle limits. And then we can add our collision constraint explicitly as a constraint to an optimization. Now this optimization is a little bit harder to solve. We no longer use just gradient descent with gradient projections for the boundaries like we did before. Instead, we're using a sequential quadratic programming technique. We're also solving for the full inverse kinematics of the robot arm while we're doing this. So we're also ensuring that any grasp we try is kinematically reachable for the robot. Okay. We can also add analytic constraints between, say, the robot and parts of the environment that we're not reconstructing, like the table, where we can just fit a plane to it and say we also don't want to run into that. Okay. One thing that this gives us beyond just being able to encode these collision constraints is we can now grasp from new viewpoints that we weren't trained at, where, say, the back side of the object is where the robot's going to put its hand. And because we're doing this 3D reconstruction, we can be fairly confident that we're not going to run into it. And so if we show an example of that, so the camera here, is it playing? OK. Well, the main thing is if we don't do the reconstruction and we try to grasp in this situation, the robot actually knocks the object over. And in our case, it picks it up. Okay. So this is currently under review at ICRA, but we're planning to put it on archive in the next week or so. My student's at a conference, so he hasn't had time to do that yet. All right. So in terms of these inference extensions, I've shown you how improving we can improve the diversity and quality of grasp by modeling grasp type. And that, in addition, adding priors to our grasp distribution improves our inference. And then we can incorporate more domain knowledge into our optimization through the use of object reconstruction and robot kinematics. Right? And I think this is one of the strongest and most underexplored areas here, is how do we add more domain knowledge without learning, or with learning, into these unified optimization approaches. Right? And the optimization tool really gives us a common language to communicate between model-based approaches and learning-based approaches. Okay. So I'm now going to talk a little bit about some trajectory optimization work we've done for in-hand manipulation. So there's not going to be any explicit learning in this part. But we're still motivated by similar problems, which is most work on in-hand manipulation mirrors that of kind of traditional grasping work, where you take some dynamics model of the object and you solve some equations for how you should apply forces or velocities on the object to make it move in the way you care about. However, if we don't have models, what should we do? And so people have looked at learning here, primarily in terms of both from vision as well as tactile, including some work I've done in the past that's shown on the right there. But in general, we found that people have a hard time learning strategies here that generalize across objects or trajectories. So you can generally get one or the other, but not both. And so we thought, well, how can we look at a kinematic planning problem, where maybe I know the 3D model of the object that maybe I've extracted through interaction using some of the techniques I pointed to before, but I don't have, say, the mass, center of mass, and inertia of the object. So we're going to take the assumption that we're given an object with some initial grasp that's stable. So maybe it was generated through the grasp planner I just talked about. Then we want to move it to some new pose relative to the hand. And we want to find the full sequence of joint angles to move from the initial to final without making or breaking any contacts on the object. Right? So we're not going to do the general grasp planning problem, but we're going to restrict it to only cases where you're not removing your fingers from the object. Okay. So this is generally referred to as in-grasp manipulation as a subpart of in-hand manipulation. Okay. So our general approach is as follows. Given this initial grasp pose and a desired object pose and initial joint configuration, we're going to find a joint space trajectory to move to the desired pose without any modeling of object dynamics or contact dynamics. And I'm going to show you an evaluation of this where it's performed actually 2,000 trials on the physical robot across 10 different objects. Okay. So our approach, like I said before, is trajectory optimization. I'm going to give you the high-level idea of what our cost function looks like. So the first terms are going to define an object pose cost. So we're going to say we want to move the object to some desired final time step configuration, xg. And then I'm also maybe going to add some waypoints in between from the initial time step to the final one to help guide that motion. Right? And we've looked at a few different ways of generating those waypoints, which I can talk about if you're interested. But then more importantly, we're going to put some cost on the grasp. And this grasp cost is going to encode both a cost on the position of the fingers and the orientation of the fingers, which we're going to use to ensure that we don't drop the object while we're moving it. Like in the grasp inference, we're also going to add constraints here in terms of joint kinematic and velocity limits. Okay. So the problem is, if we don't have a dynamics model, and I want to predict how this object's going to move as the hand moves, how do I make that prediction? And so we're going to make an assumption that is not true, and we know it's not true. And we're just going to assume that the object is rigidly attached to one of the fingers. Okay? If we do that, then it's trivial. Any joint configuration, I can directly tell you where the object is, because it's just a rigid body transformation. Right? So now if I have this goal position for this banana shown in red, I can do standard trajectory optimization to find a path for the joint angles to get that motion. Okay. But what about the other fingers? So I could add this same rigidity constraint for all my other fingers, where here I'm just going to show it with a second finger. And if I do that, I can solve this problem, but only locally. Because the fingers are under-actuated, right? There's only 4 joints, but we have a 6 degree of freedom constraint. So we're not going to have a large reachable workspace for this problem. So instead, we take this rigidity constraint for all the other fingers, and we relax it to a soft constraint. That is, we turn it into a cost, and this serves as our grasp cost function. And this you can think of as increasing the reachable workspace of the robot. Intuitively, what we're doing is you can think of, I'm going to move my thumb to the desired position, and I'm going to try to keep my other fingers as close as possible to their same configuration on the object relative to the thumb's position. Yeah?
Doesn't the wrist pose give you another 6 degrees?
It does, but we're defining everything with respect to the palm. So if I move the wrist, it doesn't change the configuration. We're looking actually that helps somewhat in dealing with like large moments. So if I like to deal with gravity, but I'm not going to talk about it in this. Okay. But so if we kind of look at what this relaxed rigidity constraint gives us when we do this optimization, you see that this cartoon version, the index finger is kind of rotating and sliding a little bit relative to the object. But as long as it stays close to where it initially was, we're going to assume it's still going to be a stable grasp. And importantly, this is going to hold true empirically. So here's the hand again. Here's kind of the range of motion to show you can see what it looks like. We're going to test on these 10 objects from the YCB object data set. For each object, we're going to try 10 different goal poses 5 times each. Right? And we're going to compare to 3 other methods. So this is 500 trials for each method. Okay. Where the other methods are kind of slightly different formulations based on things in the literature of this grasp optimization. So here's some example trajectories. So you'll see there's visual markers. These are only used for error analysis. This is a generally running open loop with respect to the image. It's just doing some feedback tracking or some position tracking on the fingers. And so you see we get pretty good tracking to this final pose. We've had a final median Euclidean position error of 1.32 centimeters across these 500 trials, and we never once dropped the object. So
we pick the contact, which is the rigid contact.
So we just say the thumb. Just without loss of generality, pick a finger.
And throughout the motion, that one is the one.
Yeah, so that's going to be we're just going to assume that's rigid. But you can see in some of these, the object's going to slide. So right there on the fork, the thumb actually slid up a little bit. So the rigidity assumption is not holding. But it's close enough that it's going to work in practice. Okay. So for this method, we can also add things like collision avoidance constraints. So here we do have vision to know where the object is, but we can move this banana around the pair without hitting it, taking standard sign distance functions as constraints between the robot and its environment, as well as the object in the environment. Okay. Right. So with this relaxed rigidity for in-grasp manipulation, we can have a purely kinematic approach to in-hand manipulation planning that directly solves for the joint space trajectory. So we don't have to do some external inverse kinematic solution. We'd solve it all at once. And through our extensive validation on a real robot, we found that it was quite reliable. Right? Never once dropped the object. Right? And I will say we tuned the gains so that we preferred not dropping to cavalier motions that would drop the object but get closer to the goal maybe. Right? But the parameters were the same across all objects. We just did a little bit of tuning, and it worked quite well. So it's pretty robust to different objects. Okay. So briefly, we wanted to move away from just doing in-grasp manipulation. Yeah, sorry.
What constraints are there on how far the goal can be from the start? It looks like these are relatively close here.
Yeah, so that's a good question. So we did some analysis in the journal version where we looked at the error relative to the distance of the goal. And so we tried to sample things that were within at least the kinematic reachability of the thumb. And we did a little bit of, if we extend that, the error will go up, but the robot will stop when it's going to move the fingers too far and drop the object. So for this analysis, they're mostly things that we're fairly sure the robot can achieve. Okay. So we wanted to start looking at doing more complicated in-hand manipulation, where we can actually remove fingers and relocate them on the object. So what's often referred to as fingertip gating. And with this, we'd like to move from some initial grasp configuration to some other configuration with fingertips at different locations, shown here in the green circles. right? And so in order to do this, we'd like to find a sequence of both hand joint configuration and object poses to move from one to the other. I'm not going to get into the details so much, but at a high level, we're going to do this with two primitives. So the first is going to be fingertip relocation. So if I have this initial grasp shown here, where the arrows show the current fingertip pose, and the red points show the desired point contact for the fingers, we'd like to move those arrows to be at those fingertips locations. But we're limited by the reachability of the fingertip. Right? I can't arbitrarily move my finger to a new position without moving all my fingers at once. Okay? But we see that for the desired grasp, we do have to be, right, we're going to have to move these ellipses somehow as well. So what we do is use these two primitives. So the first is going to be relocation of the fingertips, which we're also going to solve as an SQP optimization, which is a very simple kind of standard trajectory optimization problem. Okay. But instead of going all the way to the goals, we're going to go as far as we can for each finger without leaving the reachable workspace of each for the finger, right? So you see here, I try to get as close as I can to the red points, but I don't go any further because I can't. And then what we need to do next is relocate the reachable workspace of the fingertips relative to the object. And to do that, we can use exactly the method I just told you about. Right? I can use my in-grasp manipulation, where I slightly change what my desired configuration of the object is, to move these reachable workspaces approximated by these ellipsoids to be closer to the goal configuration. And if I can't do it in two, I can alternate this until I can. Right? And if we use, say, a geodesic to measure the distance between the fingertip and the desired location on the mesh, then we're going to converge. Okay. So here are some example plans generated for this. So we see that we get this kind of move fingers, relocate object motion. And that's great. We have a purely kinematic way of generating these plans. But what happens when we actually try to run it on the robot? Objects fall. Okay? Because we're not explicitly thinking about stability at all. To overcome this, we're currently working on incorporating some of our work on tactile feedback control. Oh, I guess that was already started. Sorry. There we go. So we can now use our slip detector to determine if the object's slipping and apply more force to correct for that, and have a stable grasp even with these outside perturbations. Okay? So look for this in the next few months, some combination of these two methods that my student Bala needs to get published because he wants to graduate in the spring. Okay. So lastly, I told you I'm going to talk about this graph neural network. I'm going to do that with my last few minutes. So this is a problem I've been interested in for a long time. Oliver mentioned in the hallway earlier, he's like, I remember you talking about this during our postdoc. Like, you really wanted to work on this problem, and I now finally have, so I'm really excited to share the results. So the idea is we'd like to move a collection of objects from some initial region to a final region. But I don't want to have to know about how many objects there are. I don't want to have to track every single one explicitly. But if you think about in the morning, you're getting ready to come to work, and you have a pile of coins on your dresser. You don't have to count how many quarters, nickels, and dimes there are to swipe them into your hand and put them in your pocket. Right? You can reason about this collection at the level of the collection. So we're going to look at that, and we're going to learn a policy that can directly operate on the image to do this. And importantly, it's going to work on the real robot. And it's also going to be able to work and generalize to different collections of objects. So we're going to train just with these cubes. But we can also, say, push silverware piles to the goal. Okay. So at a high level, how we do this is we're going to learn a latent state embedding with graph neural networks in simulation. We're then going to perform RL with that learned representation in the simulator to get a policy that works just from vision, and then deploy on the physical robot. So there's a form of what's called asymmetric actor-critic. We're going to use an actor-critic style RL, where we have ground truth information about the objects encoded from the state information in the simulator to compute our reward function. But our policy is working directly on images. Okay. And so I'll briefly tell you about the neural network structures we use. So the bottom row here is our graph neural network. So we take a set of object poses, so say 10 objects in the simulator. We know they're x, y, and theta. I then pass them through a graph neural network, which essentially allows us to take a variable number of inputs and map it to a fixed length vector that then encodes information about all of these objects. I can then use that through to learn a linear embedding to some space phi. And then I'm going to train on an output loss to do reconstruction of these poses. But because I, again, have a variable number of objects, and I would have to, if I want to do data association between each object and the output, the neural network has to learn this mapping, and I've lost the ability to deal with a variable number of objects if I try to make some fixed length output. Okay? So instead of doing a standard regression output, we're going to use what's called a mixture density network output. So we essentially, instead of just learn the parameters of a Gaussian mixture model. So the mixing weights, the means, and the covariances. Then, for each object I observe at a training time, I put the standard log likelihood cost on the probability of that object being in that pose defined by this Gaussian mixture model density. So our policy network, or the network to encode images, is going to look identical to this, except we don't know the ground truth input. So instead we take the image, and we pass it through some convolutional layers, and then pass that into the graph neural network structure. And we train on the same loss, this mixture density loss. So here's an example of what those densities look like that we learn. So under some different, both the convolutional, the image-based neural network, as well as the graph neural network. And the important thing is if we don't try to use this a multi-layer perceptron, or we don't use this MHDPA section, we do a lot worse than we do with our graph neural networks. Okay? So here's what this looks like on the physical robot. Again, this is trained entirely in simulation. We just deployed it on the robot. To get it to work easily, we made some custom end effectors that had sponges, so we could just slam the hand into the table and not have to do any sort of delicate impedance control. So the top left is our method trained with the full approach. The top right shows a slightly ablated version of our loss function, as does the bottom left. And the bottom right shows if we just try to learn a visual autoencoder without this graph neural network structure or this asymmetric actor critic, we do a lot worse. And it just kind of pushes stuff around. Okay. So we did a lot of experiments, and our method beats the other threes in essentially in all cases. Right? So this graph neural network gives us a tool to deal with this variable and changing number of objects for policies. All right. So with that, I'm going to conclude and just remind you of the contributions. So I showed you first how we can do use probabilistic inference, to combine deep learning and optimization for grasp planning. I showed you how modeling grasp type can improve grasp success prediction, and how relaxed rigidity constraints can enable purely kinematic in-grasp manipulation planning. I also showed how we can leverage that in-grasp planning to enable fingertip relocation for regrasping for planning. And finally, I showed you how graph neural networks can enable policies to reason over a variable number of diverse objects. Okay. So briefly, some future work and ongoing work we're working on. We're looking at combining our grasp planning and in-hand manipulation planning into a single framework. So we can give you an arbitrary object pose, and the robot comes up with how it should grasp it and change it in hand, while also integrating tactile feedback into the execution. We're also looking at how we can jointly plan manipulation that both improves our understanding of our object models, while also making progress towards our goals, and looking at increasing the kinds of sensors we use to include information from more tactile sensing as well as audio sensing. Okay. So here's most of the team that did the work you saw today. So importantly, so Chinkai in the top left led the grasping work. Bala led the in-hand manipulation work. And Matthew here on near the right, he did the majority of the work for the variable object pushing. Actually, I mean, he did really all the work. I just kind of helped a little bit. And then everyone else kind of collaborated to different things I showed briefly. So here are the key references, as well as my contact information. And with that, I can conclude and take any questions. Yeah.
Thank you for the talk. I have two questions. Can you talk a little bit about the benchmarking in grasp and hand manipulation page that you have on your site, or somewhere close there?
OK, yeah. So we have a page on our website. I'm surprised you've seen that, because so that's actually associated with there's a special issue of Robotics and Automation Letters coming out on benchmarking for manipulation. And we have a paper that's under review there on specifying this benchmark. And so we created that website as supplemental material. We should know sometime next month or the month after if that gets accepted. And so fingers crossed, it'll be in RAL in the next few months. Yeah.
So there was a lot of work about in-grasp manipulation with Ken Salisbury, where I think the argument was that if you have 3 point contacts, which are fully controllable on an object, then you can basically do the thing you were doing. But I saw that you were using 4 degree of freedom fingers. So is there something else that you get out of the 4 degree of freedom, or is it just a redundancy?
So first of all, point contacts don't exist in the real world. There's no such thing. Right? You always have surface to surface, even if you have 2 spheroids. So we found that none of those results really generalized. Also, when you have joint limits, right? So to get any of those models to work, you also have to know the full dynamics of the object. And so we looked at that work and were inspired by it to make us think that this might work. But I don't really have any theoretical analysis of why that is the case. I really just say, if you have some reachable workspace of the hand, and you can make grasp that kind of look like the initial grasp, then it's probably not going to fall. It's really just an empirical result more than anything. Yeah?
In the grasping work, you showed some objects where the heuristic worked reasonably well, the eval max worked a little bit better, but then the inference model worked like significantly worse. Is there any reason for why the inference model would work worse when the eval max would work better than the heuristic?
Yeah, that's a good question. So I think there's a couple objects where that happen, and I think it generally happens for geometries that are significantly different from those we saw at training. So because we're not doing anything to cover the space of kind of object shape, that if we just have a few candidates that might work, like the heuristic, and we take the best one, then we're going to be better than if we overconfidently move to something else, but it's going to be slightly different on the object.
And so did you find that the prior solves those scenarios?
Yeah, so the prior, in the form I showed you, doesn't. But there's something we're doing now that's helping a little bit more, which is we have another paper under review where we learn a conditional prior on the image. So what that means is or on the point cloud. So we say, for this object geometry, what grasps do you think are good? Or what grasp are close to grasp you've tried? So now we're looking at this closeness both in the object space and the grasp space. And that really improves it even further. Yeah.
If there's no more questions, I think we're also at the end of the time. So let's thank the speaker.